Okay. Okay, so I think we can start now. Thanks for joining us. So today we have Dr. Kamo Kamari. She is an ASP postdoc fellow at High Altitude Observatory since 2024, specialized in studying nonlinear wave dynamic within the upper atmosphere, covering regions from the equator to the polars. She earns her PhD in physics from Clemson University in May 2021 and subsequently served as a postdoctoral researcher at Arizona State University School of Earth and Space Exploration until December 2023. With 8 years of expertise in handling observational and model assimilated data, Dr. Kumari is skilled in the analysis of satellite observations, ground-based imager data, and meteor radar observation pertaining to winds associated with tidal wave scale, planetary wave scale, and traveling gravity wave scale phenomena. Currently, she is primarily interested in exploring whole atmosphere model simulation to research the role of low atmosphere wave coupling process in connecting the dynamic of the lower and upper atmosphere during moderate to active geomagnetic condition. Additionally, she is also looking into recent developed high-resolution WACOMAX to explore various sources from above and below to mesoscale variations in the upper atmosphere region. So today she's going to talk about the interaction between the geomagnetic activity and the southern stratosphere warmings. Yeah.
All right. Thank you, Chiting. So first of all, again, thanks to ASP Fellowship for providing me the opportunity to do this work. And I also want to thank my mentor, Dr. Nick Patella, for suggesting me this topic, which is interactions between geomagnetic activity and sudden stratospheric warming. So this is the outline and key discussion points that I would be focusing on. So first, I will just give some overview of ionosphere thermosphere coupling, fundamental concepts, and the relevance of geomagnetic storms and sudden stratospheric warming events to the coupling mechanisms. And in the first part of the talk, I will talk about a case event. So basically, using this case event, I want to convey how do SSWs or sudden stratospheric warming events modulate storm time responses in ionosphere thermosphere region. I'll be talking about temporal and spatial effects. So storm phase evolution, onset, main, and recovery. And then in terms of spatial effects, I will talk about latitudinal and longitudinal variability. I would talk about latitudinal dependent signatures from mid to low latitude, in thermospheric composition, plasma density, neutral winds. And then I would also talk about the mean state variability, or the background variability, and the local time variability. In terms of distinct atmospheric tidal features. And in the second part of the talk, I wanted to show some preliminary analysis results from recently developed high-resolution WACOMAX at NCAR. And I will be basically talking about some of the results during the SSW events with moderate geomagnetic conditions. So I will show some preliminary comparison with observations. Then I will talk about thermospheric wind, ionospheric electron density anomalies on mesoscales, on MSTID, MSTD scale, and the role of lower atmosphere coupling in thermosphere, ionosphere, mesoscale variations. So that's the overview of all the discussion points. So let me just start with some of the fundamental concept, which I'll be talking again and again in the next slides. So I mean, what do we know about the ionosphere-thermosphere coupling? So, as you can see from this diagram, that the ionosphere and thermosphere around above 100 kilometers, they coexist. And we have number of ions and neutrals in that region, so they both coexist. So we have one of the main coupling is due to ion neutral collisions, which can also result into ion neutral chemistry. So one of the main thing that we study in ionosphere, especially in F region, ionospheric F region, where the ionospheric electron density peaks, and the O plus ion also dominates. So, I want to just give an overview of how the ion neutral chemistry here it sort of dictates the O plus loss in ion. So, if O plus ion interacts with or collides with N2 molecule, it can generate NO plus, and this sort of results into O plus loss in the ionosphere. And if O2 plus ion, which also exists in the ionosphere region, if that collides with neutral O, atomic O, it can generate O plus. So that's kind of a mechanism to gain O plus. So this is one of the main mechanisms that we study, especially in thermospheric F region, how the O plus ions loss and gain is modulated by the O atomic oxygen O and the N2 molecule density or composition. So another important aspect of ionosphere-thermosphere coupling is the electromagnetic dynamic processes. So I will be talking about in the next slide 2 concepts here. So one is E cross P transport. So I mean, we have in the ionosphere, we have electric currents and also Earth's magnetic field. So especially at equatorial region, when the magnetic field is horizontal, like northward, and the electric field is eastward, that generates a E cross B force, which sorts of pushes the plasma away from the equator at 20 south and 20 north. So this is one of the main electromagnetic force, I would say, it exists, which transports the plasma. And another important dynamic process that exists is perhaps this animation is pretty, like, it makes it easy to understand. So the wind, the neutral wind, can push the ions along the magnetic field lines up and down. So that's called field line transport. So these are some of the fundamental fundamental mechanisms that I will just talk about in the storm and SSW concept. Okay, so any variations in the ionosphere and thermosphere region, we study that like as space weather, and storm and sudden stratospheric warming events. They represent for strong forcing from above. In terms of storm, it's a strong forcing from above, and for sudden stratospheric warming, that can be considered as the strong forcing from below. It's coming from troposphere and stratosphere region. So for storms, I don't need to explain what storm. People are more expert than me here. So generally, the storms are triggered by coronal mass ejections or a high-speed solar wind stream, and generally the Kp index greater than 5. We consider that as a storm condition. And the key effects of the storm, we know the aurora or northern lights. Then in terms of technology, we can have satellite path disruptions, GPS and communication disruptions, power grid failures, radiation exposure. Let me give a little more descriptive analysis for sudden stratospheric warming. So sudden stratospheric warming is basically in the polar stratosphere region, due to increased lower atmosphere waves, sometimes almost every winter nowadays. So what happens when these low atmospheric increased activity of lower atmospheric waves, when they reach to stratosphere and dissipate, they can slow down the polar jet, and sometimes even reverse. So and as it is slowing down the jet, the wind can descend and get adiabatically heated. So the way we detect sudden stratospheric warming event, we analyze the stratosphere temperature and the zonal wind in the east-west direction. And whenever we see the temperature suddenly shooting up to like 50 degree Celsius, 50, and then the wind sort of slowing down or even reversing. So in case of complete reversal of the wind from eastward to westward, it's called major sudden stratospheric warming event. So this is one of the main indicator of that the sudden stratospheric warming is going to happen. And due to this event, what happens, the tropospheric jet stream becomes wobbly, and some of the cold air from polar region starts to penetrate to mid-latitude. I mean, in Boulder, I have myself experienced some of severe winter storm because of this sudden stratospheric warming event. And as I said, it happens almost once every winter. So some of the key effects of sudden stratospheric warming, as I said, the polar vortex breakdown, jet stream distortions, extreme surface weather. Then it is also, in terms of dynamics, we also study the sudden stratospheric warming event to study tropical and polar coupling. And they can also disturb, chemical transport, mainly for the ozone chemical transport. And as well as there are numerous studies which explain how the sudden stratospheric warming event can also cause ionospheric disturbances. So I'll explain some of that now. So here, for the first part of the study here, I'm going to talk about the case study of 27th February 2023 storm. So KP was 6 at this storm, and the storm pretty much occurred at the same time when the wind had reversed in the stratospheric polar zonal wind went from eastward to westward direction. So pretty much a peak of SSW event is when the storm occurred. So this gives us a wonderful opportunity to really study how does the space weather behaves when there is a strong forcing from both above and below. This is also inspired from one of the study from Nick Pentala's 2016 paper, where he worked with a contrived scenario from a Tygesium simulation. He studied how a severe geomagnetic storm with KP equals to 9 impact may vary if it occurred during major SSW. And he found out that the total electron content, TEC, which we measure as the ionospheric composition. So that can differ up to 50 to 100% if in terms of storm response. So that was one of the main motivation to really study this real-time event. And also this gives us an opportunity to highlight the importance of how the low atmosphere forcing such as SSW can precondition the atmosphere and can precondition the storm impact on space weather. So I wanted to just give a short overview of how the ionosphere and thermosphere behaves in storm and SSW conditions. So let me first talk about storm. So I'm here just showing the GOLD and COSMIC 2 GIS data simulation data here for the 27th February 2023 storm. So here, so as I explained before that one of the main mechanism in aphorism, we study the O plus ion gain and loss by looking at the neutral composition, mainly N2 and O. So basically, the gold satellite gives us O2N2 ratio, like column integrated O2N2 ratio. So this is how it looks like for 2023 storm period. I mean, we know that during storm we have joule heating at high latitude and the equatorward transport of O2N2. So there is from high latitude to mid to low latitude. So that's why you see some decrease at mid to high latitude and an increase in O2N2 at lower latitude. This is from the COSMIC 2 GIS TEC data. This is at a certain 230 longitude. I'm showing here some TEC decrease at this longitude that COSMIC 2 sees at the during that storm. And here I'm showing the longitudinal variability of TEC variation, and this is with respect to the quiet day, so just a day before. So with respect to non-storm conditions. So this basically shows that TEC not only increase but can also decrease at certain longitude. So that's called positive TEC anomalies and negative TEC anomalies, and that can really positive can happen because of enhanced ionization or storm time electric fields, and negative anomalies can happen due to increased recombination, which can also happen during storm, and also altered plasma transport. So some overview of how ionosphere thermosphere may behave during SSW. So I'm just citing some of the previous studies which has recorded the SSW response to ionosphere and thermosphere region. So this is a plot from GOLD into data only from Oberheide et al. 2020 paper, where he found that O2N2 can deplete, and I think the number was up to 10% with respect to background. And this was the case of January 2019 sudden stratospheric warming. So that's basically because of upwelling towards the from equator to poleward direction of O poor air, atomic oxygen poor air, and also associated with the residual mean circulation changes. And then in terms of TEC, how SSW can change TEC, this was a I think pretty famous study from Larissa Goncharango of ETL 2010 paper, where she saw in GPS data that the TEC can vary during SSW, like during morning hour, like with respect to background, can increase, and in the afternoon it can decrease. So this is in terms of local time effect. And that is mainly due to enhanced E-cross speed vertical drift during morning time and decreased during the afternoon time. So, all right. So now that we, hopefully I could give enough explanation of how the both storm and SSW impacts ionosphere and thermosphere. So now for this study, I want to study how they both are impacting and how SSW is further impacting the storm response in the ionosphere thermosphere region. So, okay, so for the analysis, I'm using SD-WAGM-X run. So I'm using 2 runs here. So the first run is just the general. I have the realistic lower boundary condition with SSW, and I also have the storm condition from above. In the second run, I attempt to remove the SSW condition at lower boundary, and lower boundary is nudged from the MERA2 data. So to remove the SSW effect, I basically take the 40 years of MERA2 climatology, and that is what I use to nudge the lower boundary condition. So not only I removed SSW effect, but I also removed day-to-day variability that's coming from below, and perhaps some annual variability impact as well. So this is just an example of how the lower boundary for first run and the second run looks like. So that's how the climatology looks like. All right, so here I'm showing at mid-latitude how the column O2N2 variability looks like in 2 runs. So this is O2N2 and this is TEC, again, total electron content. So as I explained before that at mid-latitude, the O2N2 decreases during storm. So that's what we see in both runs, and TEC can increase or decrease, but at this here it shows that it is increasing during the storm. So but one thing I want to point out that these 2 runs have some sort of seasonal trend in offset, like the offset had some seasonal trend, and that is mainly due to the nudging the lower boundary condition in the second run, because I'm really removing day-to-day variability as well as some interannual variability effect. So to really, I'm not interested in this offset. What I really want to study is how the SSW impacts storm response. So what I do, I calculate the relative storm response in both runs. And for that, I just subtract with respect to just a previous quiet day, so storm occurred on 27th. So I subtract the O2N2 and TEC data with the 24th and 25th February when the KP was less than 3. So this sort of gives me, helps me to get rid of offset, and as well as helps me to understand what is the real storm response against the background in the ionosphere thermosphere region. And my goal is to really compare those 2 relative storm response in these 2 runs to understand the lower atmosphere preconditioning effect that's coming due to SSW. So here I'm showing the relative storm response again. So in the top, I'm showing the O2N2. The bottom, I'm showing the TEC. So, the first column is from the first run, and the second column is from the second run, where I have removed the SSW. And here in the plots, I am also showing the red line plot, which is actually KP index, which shows you when the storm actually occurred, right? So it was pretty much on whole day on 27th February. All right, so hopefully just by eye, you can see there are some differences in these 2 runs in terms of storm response in O2N2 as well as TEC. But one of the main thing you can see that there's a sort of storm recovery period even after the KP has gone below 4. So there's this whole recovery period on 28th February. And if you see that the storm recovery is different, especially it's more visible in TEC, that storm recovery is slower when we remove the SSW in the lower boundary. So that's one of the first analysis that we can do from these plots. Another is that I want to evaluate how much change we are talking about. So what I'm doing here, I'm showing here line plots, mainly averaged at the low latitude. So 30 south to 20 north for O2N2 and 40 south to 30 north for TEC. And then these 2 line plots are from 2 different runs. So what I see that almost 20 to 50% change in the storm response and the faster storm recovery, both happening due to this lower atmosphere preconditioning effect due to SSW. Just want to mention one thing. So from the next slide, I will not be showing the separate result for both runs, but to really just focus on the lower atmosphere preconditioning effect, which we want to explain, I'm just going to show the difference of these two runs. So that's what I call lower atmosphere preconditioning effect. One another point that I want to make here, that if you look into TEC, when the storm was just onset, in the beginning, you have some increase at high latitude, and that is mainly due to direct particle precipitation. But slowly it descends to low latitudes, and that's mainly because that we understand that already we understand that from other storm studies that these low latitudinal TEC responses mainly due to the thermospheric compositional changes, as in O2N2 changes, and as well as the disrupted plasma dynamics, which I explained before, the E cross B and the field aligned transport that happens due to electric and magnetic field effect. So in the next, I will be mainly focusing on the 28th February, which is the storm recovery period, to really explain what's really happening at the low latitude. So here, first I am going to talk about some mean state changes. That means I am showing 24-hour mean, right? So no tidal variations or such. So here I'm showing diurnal mean or mean state during storm recovery, so on 28th February. And I want to sort of try to understand how these changes in O2N2 and TEC are connected, because we already know from some previous studies that O2N2 impacts TEC, the O2N2 changes. So here I am showing the difference of two runs, as I said in the last slide, and I'm showing that with respect to all the latitude and all the longitudes. So spatial variability, sort of. And here, this is for TEC, and I'm also showing NMF2, which is basically peak electron density. And just want to say one thing, TEC is basically total electron content, which is height integrated electron density in the ionosphere region. And NMF2 is more peak electron density. So I'm only plotting here the electron density at F region peak at around 250 kilometer, give or take. So here, probably if you just look into O2N2 versus TEC, it's not that apparent how the O2N2 might be impacting TEC. But if you look into the peak electron density, it's pretty clear that O2N2 is impacting the peak electron density, especially at mid latitudes. And I forgot to mention that the most O2N2 lower atmosphere preconditioning impact in O2N2 that we see is mostly at over mid latitudes, northern mid latitudes. What's happening at low latitude? As I mentioned, that it could be due to some plasma transport mechanism, E cross P or field aligned. So one thing I want to point out that any change in NMF2 would also change, or in peak electron density would also change critical frequency FOF2, which is important parameter for radio communication. So that just, I thought I should mention that. But now getting to the low latitude effect that is not coming from O2N2, that might be coming from SSW effect on the plasma dynamics, and that could be because SSW impacts the may impact the mean neutral wind in terms of both zonal and meridional direction. So this was from one paper I found, Gong et al. 2013, where he basically used Arecibo incoherent scatter radar observation to show how the SSW may impact at low latitude, how it may impact the eastward wind in E region and southward wind in both in E and F region. And these winds are important for the plasma transport mechanisms. So to really get into more detail of how this chemistry and transport term are sort of working, and what is their relative contribution to overall TEC change at low latitude, I further look into ion continuity equation of O plus. So O plus an electron changes follow the O plus ion changes in the ionosphere F region around 250 kilometers. So where the electron density peaks. So that's why we can look into how the O plus ion this transporter chemistry effect, how they are changing the O plus ion, and maybe that would also explain how the electron density or TEC is changing. So just to, before I go further, in the ion continuity equation, we have production and loss term, which basically talks about the chemistry part. And then then in the ion continuity equation, we also have E cross P, the vertical drift part, and also the field aligned drift part that I explained in the first few slides, the field aligned drift part. So we can really look into all those, and there's also the diffusion part that acts to change this O plus, but I mean, I did not find it much significant, so I'm not going to discuss the diffusion part here. All right, so this is just a busy slide, but but I just want to explain all of this in one slide. What's happening with respect to why do we see those preconditioning effect in O2N2 as well, right? I didn't explain that. Why do we see the O2N2 effect at mid latitude due to SSW? And then I would also explain what is happening at low latitude in terms of total electron content or electron density. So let's first look into the O2N2 changes. So we know during storm that at high latitude due to Joule heating, you have this adiabatic heating and increased upwelling, so increased vertical wind at high latitude, and then due to the meridional transport, the O2N2 is basically transported at lower latitude. So both the meridional circulation in thermosphere and the vertical wind both are important for O2N2 changes during storms. So I looked into the similar, plot for vertical wind as well as the meridional wind. So this is again the subtracting both runs in storm conditions. So what I found that the vertical wind, especially above F region height, that's where I found that vertical wind seems to have one-to-one anti-correlation. So if you really see the color bar is reversed here. So red is basically negative, and here yellow is positive. So there is anti-correlation, and similar for meridional wind. So with the same mechanism that I explained, that the upwelling kind of results in decreased O2N2, and downwelling at lower latitudes results in increasing O2N2. So there is already this anti-correlation effect that we already know, so that this kind of confirms. And I also wanted to show, okay, so before I go into why SSW affects this vertical wind effect, right? So as I explained before, that SSW can decrease O2N2 ratio, mainly because from equator to poleward transport. So it's opposite of what happens during storm. During storm, you have from pole to equator ward, while during SSW you have opposite side sort of effect on the circulation. So maybe that is why we have the vertical wind changing O2N2 on one-to-one anti-correlation basis. And then, as I explained, that O2N2 is what explains the gain or loss of O plus ion. So I also checked the production term of the ion continuity equation of O plus and below the F region where the production and loss is dominant. So I saw that the O2N2 indeed has one-to-one correlation with the production term, and also the loss term. I'm not showing that here, but so now that we understand a little bit that O2N2 is mainly coming from the vertical wind changes due to SSW, as well as it seems like the meridional wind also follows some of these positive and negative with respect to vertical wind. So I believe that both meridional circulation and the vertical wind both playing role in the O2N2 changes. Now looking into what causes the TEC change at low latitude. So so this is the TEC change that I showed in the last slide. So to really explain what's going on with TEC, I looked into electron density. So TEC is height integrated electron density, but to really explain, I had to look into electron density above F region. So during storm, the electron density peak can really be pushed upwards in altitude. So I looked in above F region, and what I found that indeed the transport, so this is the total transport term, so E cross V transport and the field aligned wind transport, which I show here separately. But when you add these two, this is what you get, so net transport effect. And so this seems to be explaining some of what is happening in terms of electron density at low latitude. And above F region, the production and loss term is small, so that's why this transport term starts to really dictate the electron density changes. One thing I want to point out that if you really see that the E cross V transport and the field aligned transport both look somewhat opposite of each other at some longitudes, but the net transport effect seems to be more correlated with the E cross V transport. So perhaps the E cross V transport is more dominant. This is all right because we know that the SSW can change can have impact on the electric field changes, which also impacts the E cross V vertical transport. So now that I talked about the mean state changes, I also want to show the local time variations, which can happen due to SSW, which can impact the storm response. So here I'm showing again the electron density change with respect to latitude and the UT, so all 24-hour in terms of universal time, and I'm showing the net transport term effect with respect to latitude and all the 24-hour local time. And this I'm showing for 3 longitudes. So one 40-degree east, another 140-degree east, and then 140-degree west. So one main thing I want to point out that what I saw, at least at 40-degree east and 140-degree east, that the local time variability seems to be mainly due to SSW. It's mainly happening during nighttime. And it seems more sort of 6 to 8 hour variation from peak to deep, if you see. So it seems like more like diurnal tidal sort of variation in terms of the local time effect. And then at 140-degree west, I also saw that some semi-diurnal tide like variation. So this was interesting to me. I mean, there have been studies before that the SSW amplifies both diurnal and semi-diurnal tides. And it seems like SSW preconditioning is mainly happening during nighttime. But I also, to really explain whether the local time variability is coming from E cross B transport or the field aligned transport, I actually found a study from Gong et al. 2013 paper, and used similar data for Gong and Zhou 2011 paper as well. So there they showed that this was from 2010 SSW, that during SSW, the third diurnal tidal, which is this peak here, can be really prominent above 200 kilometer, even more prominent than semi-diurnal tides, which is at frequency 2 here. And this is frequency equals to 3 is the third diurnal. This makes me think that since the third diurnal tide probably is being amplified at higher altitude above 200 kilometer, makes me think that probably the field aligned transport in the F region is probably is the reason why we see the local time variability, because the E cross B is mainly being set at the E region below 200 kilometer, around 120 kilometer. So I also compared the field aligned wind with the local time variability with the transport term local time variability, and they do look aligned, at least for 140 degree east and 140 degree west. Some variability at 40 degrees. So, but that's what my some of the conclusion that the low atmosphere preconditioning during SSW is probably causing 20 to 50% variation to the storm response in electron density and O2N2, and also it's causing faster recovery after storm. Then electron density changes during storm recovery predominantly occurs low to mid latitude. Some of the mean state changes at mid latitude is mainly coming from thermospheric composition changes, O2N2 changes through ion neutral chemistry. And at low latitude, the mean state changes mainly coming from vertical transport, electric fields, and I think some role field aligned transport is also playing some role, but mainly the electric field vertical transport. And the local time variability at low latitude seems to be more coming from third diurnal as well as semi-diurnal winds in field aligned winds. And then the O2N2 variations that is happening due to SSW in storm response is mainly preconditioned by vertical wind changes at mid latitude. So this was the first part of my talk. In the second part, as I said before, that I would like to talk about some of the high resolution Wacom simulation results of mesoscale variation in thermosphere, ionosphere during SSW. So let me give a little bit overview of what do I mean by mesoscale disturbances. So from number of ground-based observations, we have studies that the medium scale traveling atmospheric disturbances in thermosphere neutral winds, which are called MSTADs, and the medium scale traveling ionosphere disturbances in ion electron density, which is called MSTIDs. They both exist, and the kind of spatial scale they have is up to 200 to 1200 kilometer. And in terms of temporal scale, they can have 15-minute to 1 hour periodicity. And they systematically exist. They have been observed by a number of ground-based observation from equator to pole. And they are important because they can change up to 10 to 15% of GPS total electron content. So it's really important for prediction accuracy of the TEC. And the MSTADs, mainly in thermospheric neutral wind, they are known to be associated with both forcing from above, so like aurora, Joule heating, and then the second, it can also have significant forcing from below, so tropospheric, stratospheric gravity waves. But in general, the source of day-to-day variability remains an open question because of lack of global observation, I would say. So one thing I want to point out that there was this study from Frisell 2016 paper where he studied the MSTID day-to-day variability from superdarn data. And he found out that at mid to high latitude, the MSTID, or this mesoscale variation in electron density, increased with 15 to 20 days delay. So I'm just showing that the superdarn, there are a number of superdarn incoherent scatter radar instruments all over this mid-latitude region over US and Canada. And he basically used the data from all these instruments and found out that so this is from 2012-13 SSW. So SSW happened around 6 January, and he found the dip in MSTID index happening much like after 15 to 20 days later. So generally, we know that during SSW, as the polar jet like slows down and reverses, so that sort of filters some of the waves coming from lower atmosphere. So but what I was not able to understand from this result, that why the 15 to 20 days delay. So I thought I would investigate that from high resolution Wacom simulation and really look into the global observation and really explain and also make an attempt to understand how the ionosphere and thermosphere are coupling on mesoscale during the SSW condition. All right, so here I'm showing the two SSW event analysis from high resolution Wacom. So here on top, I am showing the MSTID in total electron content. So this is global characteristics. So this is for 2012-13 winter, and this is for 2018-19 winter. And for in 2012-13, the SSW was onset on 6th January. And in 2018 winter, the SSW was onset on 25th December. And then in the second row, I am showing the MSTIDs at mid-latitude where the superdarn data observations are available, just for the comparison with the observation in the model. And in the bottom, I'm showing some of the superdarn plots, which I have somewhere stored from 2 years before when I talked with Nathaniel Frisell. So sorry for the bad quality of the plot. But what I want to show some of the important observation that I saw, that in terms of global characteristics, if you see that just when the SSW starts, it seems like in the lower latitude, the MSTID is increasing, both in the 2012-13 winter and 18-19 winter. That's just after the SSW onset. And at over mid-latitude, this is the same plot from here, but zoomed over mid-latitude. So the decrease that you see here, it is delayed in both cases, just as what superdarn observed. So here I forgot to highlight, but this is the decrease that superdarn observes, and this is around the same time that the high resolution Wacom simulation also shows. So that's interesting that the observation and the model are sort of in agreement. But one thing was very interesting to me, that there's this sort of increase at low latitude before this dip at mid-latitude, right? So two things are happening: increase at low latitude and decrease at mid-latitude much later with 15 to 20 days delay. And one thing that I want to point out before I move on to next slide. So in the high resolution Wacom simulation, I have hourly data. So I cannot really do 15-minute to 1 hour filtering, which is what the observation does. So in high resolution, basically I'm doing spatial filtering. So I'm filtering 300 to 1200 kilometer scale at each hour. And then I'm taking the zonal mean, so this is basically the spatial characteristics of MSTIDs. And in the observation, what you have is the filtered 15-minute to 1 hour, so temporal characteristics. So it's nice that the both spatial and temporal characteristics shows this the dip in MSTID at the same time. So all right, so then I went further to really try to understand what's happening at mid-latitude, why the dip is delayed 15 to 20 days. So here I'm showing the line plot, so from the contour plot that I showed in the last slide, and I'm focusing 2018-19 SSW. So this is the line plot at low latitude, and I'm comparing that with the stratospheric zonal wind, which shows when the zonal wind reversed, and that's when the MSTID at low latitude increased. And then this is at mid latitude, and here I am showing the comparison with KP index. So I think it's pretty visible that day-to-day variability is definitely coming from KP index at mid-latitude. But this decrease that I'm talking about is definitely coming from SSW. That was probably more visible in the contour plot. So, all right. So to try to understand what's happening at mid-latitude, right? So I did control simulation in high-resolution Wacom with constant KP and F10.7. So now this is the same at low latitude, mid latitude, the same plot. At low latitude, I see the similar characteristics, what I saw in the first run. At mid latitude, now that I have removed day-to-day variability coming from KP, now it really shows what is the contribution from SSW really at mid latitude. So again, the dip is delayed. It shows at the same time as the first run. But one interesting thing that I saw, that there is this increase that is happening at the same time when the increase is happening at low latitude. So perhaps that is what is happening, that MSTID increases first due to SSW, and that is why the delay is showing later at the mid latitude. So these are just the preliminary results. So now I'm talking. So far, I was talking about the mesoscale variation in electron density, right? Now, to really understand where does the thermosphere coupling coming here, and why there is this increase happening, right? So maybe that's coming from thermosphere ionosphere coupling. So I looked into thermosphere zonal and meridional wind. So and this is the MSTAD. So again, the 300 to 1200 kilometer filtered data on MSTAD scale in the zonal wind and the meridional wind. So this is from the first run, and this is from the control run. So what it shows that the zonal wind and meridional wind both shows this increase in MSTAD, but in southern hemisphere, right, during SSW. So I want to point out that the polar jet disruption is happening in northern hemisphere, but the MSTAD increase that you see is in southern hemisphere, and that's also showing in the control run. So definitely this has this has the source coming from lower atmosphere, especially during SSW. I also looked into, so this analysis is from thermospheric wind at F region. So I looked into height analysis, whether it's really coming from below. And I definitely saw this increase from E to F region, So it seems like in terms of coupling, probably no, both, E cross B or the field aligned transport, both may be acting as a coupling mechanism here, because we see the increase at the same time in electron density as well as in the thermospheric winds. I also looked into so this increase is around before 5th January. So I looked into 2 to 5th January 2019, the local time variability, right? And what I see that in terms of local time, this MSTAD increase is happening, twice, so these 2 peaks, so semi-diurnal nature. And that's okay because we know that SSW is closely connected to semi-diurnal wind amplification, semi-diurnal tidal amplifications. So at this point, I have to do more study to really understand how the semi-diurnal tidal effect from SSW is linked to this MSTAD and MSTID variation, both at low latitude and in southern hemisphere and northern hemisphere. So one thing I wanted to point out that the semi-diurnal tidal amplification during SSW event has 2 different sources. So one could be the solar semi-diurnal tide, and one is lunar semi-diurnal tide. So, both mode from the solar semi-diurnal tide and the lunar both are amplified during SSW, and both have different mechanism. So lunar semi-diurnal tide is mainly being amplified due to the resonance effect. It's called atmospheric Picker's mode. That is what is amplified. And semi-diurnal tide is mainly coming from nonlinear interaction with enhanced stationary planetary wave activity during SSW, then changes in ozone forcing and propagation conditions. So it's interesting that there may be some connection to this MSTAD, MSTID, and the tides, and which is further, I need to study how this wave-wave interaction is sort of playing role in thermosphere ionosphere coupling on meso scale. So that's my final conclusion, that that STID decrease at mid-latitude due to SSW delayed by 15 to 20 days in the high-resolution Wacom simulation is in agreement with Super Darn observation. And at low latitude, I see some increase in MSTID in the EIA region, which coincides with the increase in MSTAD in thermospheric wind, especially in southern hemisphere for 2018-19 SSW. And it may be correlated with semi-diurnal tidal amplification, which needs further study. So, yeah.
Come on, so we are almost running off the time, but yeah, one thing.
I have a couple of quick questions. When you run the model, are you using KD driven or use MF to drive one model? So what is your highlighted driver?
Well, it's the ST Wacom X in the ST Wacom X simulation.
Yeah.
That's something. I thought it's a self-consistent model, so
Yeah, just how do you put the magnetic forcing into the high latitude? What's the model you use?
Helix or one.
If I saw it's a AP. Okay, great. And then second question related to how you define MSTID.
yeah.
So you study MSTID, your wavelengths, your frequency. How you define your MS?
So MSTID, as I said, that it has both certain spatial and temporal characteristics.
Yeah.
So I mean, if you have data, every 5 minutes, you can just temporarily filter 50.
I'm just talking about the model
In the models, I have hourly data and I have high resolution data, so which can resolve dynamics up to 200 kilometer. And MSTID has the spatial characteristics, so its wavelength can vary from 200 to 1200 kilometer scale. So I basically, what I do at each latitude, I do the filtering along all the longitudes. So basically, I convert in terms of distance in kilometer, with a reference point at a 0 longitude, and then I filter the 300 to 1200 kilometer amplitude. So yeah, that was the best I could do from.
Okay, yeah, that's related to my next question is, what do you mean by global mean MSTID? Because MSTID is localized, it cannot be global. What do you mean global MST? In one of your slides, you talk about.
So when I say global mean, because what I'm doing as I'm filtering, as I'm filtering, I'm taking the. So basically, I'm doing the. I did the FFT, and then I took the average of all the longitude in terms of to get the overall amplitude.
But in this process, you may suppress MSTID because it's localized. Say it's occurring when, say in America, may not say in Asia, but you do longitudinal.
Average, so I cannot really say where it is amplifying, at which location. So I did very much like a.
I just don't curious about it.
Yeah, like a very high level analysis. I did not really go into different locations or yet.
Yeah.
So that's something I need to do later on when I am doing more detailed study of how tides and MSTIDs may be linked. I think then I will have to look into different separate reasons. Yeah.
So, sorry.
No, go ahead.
Our questions are really interesting talk. So the delay, do you know any mechanism for why delay 16 days? Or that's
exactly what is my speculation at this point, especially with the control run. I see this. I see when I did the control run that the MSTID variability at low latitude looks similar to what's happening at mid latitude, and this increase, it's my speculation. It's coming from some of the thermosphere ionosphere coupling, because thermosphere also shows the same increase in the winds. So at this point, I cannot say exactly what's happening, but that's why I told it's a preliminary analysis and not much understood. But it's interesting that I think it has to do with maybe the thermosphere summer to winter circulation is sort of pushing some increase from, I don't know.
Yeah, I thought maybe it's a low atmosphere because the thermosphere not has a 16-day memory, so it's not going to say remember what's being happened 2 months or 2 weeks ago or something like that. Maybe it's, but I don't know.
Yeah, but I also cannot say for sure what's happening, but this is just my speculation that it has to do with thermosphere ionosphere coupling.
Thank you.
Yeah, I think we have one question from online people. Do you want to mute yourself? Oh, that's I don't know. Arunima?
Hi, Komal. Very nice talk. Just a quick question, like, do you know how similar or how different the preconditioning is due to like minor versus major SSW, and anything like different between the northern hemisphere versus southern hemisphere SSW? Thank you.
Yes, I think what the case that I showed was a major SSW, which showed 20 to 50% difference, and I believe minor, because the minor SSW can also have impacts on especially semi-diurnal tides, and so I think there would be some effect, preconditioning effect from minor SSW. I cannot say how much because I did not analyze it. And another question, you said the northern versus southern. The case I analyzed was with the SSW in the northern hemisphere. So I saw a lot of changes in O2N2, especially in the northern hemisphere. So perhaps the southern hemisphere one, SSW will have more impact on the southern O2N2 mid-latitude region. So I can only like guess, but since I've not analyzed, so I cannot really say much. Yeah.
Yeah, any other questions?
Just real quick, you said that you use hourly output. You said that the MSTID, MSTAD is like 15 minutes to 1 hour.
No, so that's what. So 15 minutes to 1 hour. Okay. So in the high resolution Wacom simulation, I'm only doing spatial filtering. I cannot do temporal filtering because I have hourly data. But I compared the high resolution model simulation data with the super darn observation where they did the temporal filtering because they had more high temporal observation. And that's why I said it's interesting that both temporal and spatial characteristics show the same results in terms of MSTID decrease at mid-latitude. Yeah. So, but yeah, for high resolution to do temporal filtering, I really need 5-minute analysis.
Yeah.
Which is that's a lot of analysis.
A lot of data.
That's why I made an attempt to do this analysis with the hourly data so that maybe it can help us to do some of the quick analysis just doing hourly high resolution Wacom simulation with less, time.
Okay.
Yeah.
If there's no further question, let's thank our speaker and call for day.
Thank you.
That the TEC initially increased and then actually decreased. Increased.